Hello, everyone. Welcome to the webinar. I'm Ann Thayer, contributing editor to the CNN Media Group, and I'll be moderating today's event. This webinar is entitled MALDI-MS Spectrometry of Synthetic Polymers and is being sponsored by Bruker. CNN works with sponsors to identify topics of interest and value to CNN's audience and consistent with CNN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. First, just a few technical notes. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of the screen or type your query into the Q&A box. If you're disconnected during the webcast, please log in again according to the instructions you received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I'll be posing as many as time permits. Please note that CNN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at CNN Online after the live webcast. The presentation today is being sponsored by Bruker. Bruker enables scientists to make breakthrough discoveries and develop new applications that improve the quality of human life. The company's high-performance scientific instruments and high-value analytical and diagnostic solutions enable scientists to explore materials at molecular and microscopic levels. In close cooperation with its customers, Bruker is enabling innovation, improved productivity, and customer success in molecular research, microscopy, and nanoanalysis, as well as in industrial applications. During the presentation, we'll hear from Chrys Wesdemiotis. Chrys completed his PhD at the Technical University of Berlin in 1979. After a postdoctoral fellowship at Cornell University and military service in Greece, he returned to Cornell as a senior research associate in 1983. In 1989, he joined the University of Akron, where he is currently Distinguished Professor of Chemistry, Polymer Science, and Integrated Bioscience. Research in the Wesdemiotis group focuses on the development and application of mass spectrometry methods for the characterization and imaging of synthetic polymers, advanced materials, and polymer biomolecule conjugates and interfaces. Chrys is a AAAS Fellow and the 2019 recipient of the George Stafford Whitby Award of the ACS Rubber Division. He has served on the editorial boards of several scientific journals, and his group has over 300 peer-reviewed publications. I'll now hand things over to Chrys.
Thank you, Anne. My talk concerns mass spectrometry characterization of synthetic polymers, and in mass spectrometry we do chemical analysis by first ionizing our sample into gas phase ions. We have to convert our sample into gas phase ions. Then we measure the mass-to-charge ratios of those molecular ions to determine their elemental composition. For example, if we measured mass 18, everybody would know that this was water, and we can do that similarly with synthetic polymers or other types of molecules. If we want structural information, we have to select one specific molecular ion and fragment it into fragment ions. The mass-to-charge ratios of the fragments are then determined, and from them, the connectivity, that is the primary structure or architecture or conformation of the product, is determined. The key step in every mass spectrometry analysis is conversion of the sample into gas phase ions. And here in this slide, I list methods that can be used to ionize synthetic polymers: secondary ion mass spectrometry, atmospheric pressure chemical ionization, electrospray ionization, and matrix-assisted laser desorption ionization. From the methods I listed here, the most successful one for synthetic polymers and the one that's most widely used for this reason is MALDI. And on the bottom here I list why. Because it's applicable to a wide range of polarities, and we have polymers that span a very wide range of polarities. It's also applicable to a wide range of molecular weights, from oligomers to very large polymers. And finally, MALDI does not require solubility, so we can apply it also to insoluble polymers. Another advantage that's not listed here in this slide is that in most cases, MALDI leads to singly charged ions, which makes spectral interpretation easy because then the mass-to-charge ratios that we read from mass spectra are identical to masses. As I mentioned a few slides ago, if we want to have structural information from a mass spectrometry analysis, that means if we want to have something beyond elemental compositions, then we have to break our sample into fragments, and we do this in tandem mass spectrometry experiments. And here is how that methodology works. We first ionize the sample and measure a mass spectrum, that's MS1 stage. From the distribution of ions obtained, we select one, and we cause this to fragment most frequently by collisions, that means thermal or mechanical activation. Then in a second state of mass analysis, we measure the mass-to-charge ratios of the fragments to obtain the tandem mass spectrum. From the fragments, then, we reconstruct the primary sequence, or we derive information about the architecture or topology of the polymer. The sample preparation for MALDI-MS spectrometry analysis is simple. We form a solid solution of the sample in the matrix, and the matrix is a small organic molecule that absorbs at the laser light wavelength used. There are many different ways we can form this solution of the sample in the matrix. We can form solutions in a liquid solvent of both of them and mix those solutions and allow the solvent to evaporate, and we end up with a solid mixture of the sample in the matrix. Or if the polymer is insoluble, we can mechanically mix matrix and polymer and apply a few crystals onto the moldy target plate. The matrix is the solvent, so it's used in 10,000-fold or even larger molar excess. So then we irradiate that sample with laser light, and matrix absorbs light, gets desorbed and evaporated, and in this process carries with it also into the gas phase the polymer. The matrix is also ionized at the same time, and matrix ions transfer charge to the polymer molecules. That's usually a proton. If the polymer is not basic enough to be ionized by proton transfer, then we usually also add some cationizing salt, such as a silver salt, if we have a polymer rich in double bonds and aromatic rings, or an alkali metal salt, such as a sodium salt, if we have a polymer rich in oxygen atoms. And then the polymer is ionized by either silver ion or sodium ion adduction. Actually, I have to say at this moment that most synthetic polymers are ionized by metal cationization, not by protonation, unlike most biomolecules. A powerful instrument design for MALDI mass spectrometry and MALDI tandem mass spectrometry of synthetic polymers is a tandem time-of-flight mass spectrometer, such as the Bruker Ultraflex shown here. Bruker actually offers many other configurations of this type of instrumentation. A MALDI tandem time-of-flight mass spectrometer contains a MALDI source and two time-of-flight mass analyzers, usually a short linear time-of-flight mass analyzer, TOF1 or mass spectrometer 1, and a reflectron time-of-flight mass spectrometer, which acts as mass spectrometer 2 or TOF2. For regular mass spectra, both TOF1 and TEF2 are combined and are used as a single reflectron time-of-flight mass spectrometer. For tandem mass spectra, the short linear TOF1 is used for precursor ion selection, and the reflectron TOF is used for fragment ion analysis. MALDI mass and tandem mass spectrometry have become widely used in synthetic polymer analysis because of the wealth of information that these methods can provide. We can use these methods to determine the compositional heterogeneity of synthetic polymers, which means we can determine both major and minor products. Sometimes the minor products cannot be determined by methods who analyze bulk, but in mass spectrometry, where we can analyze individual oligomers of a polymer, we can easily detect minor components. And so the method is very powerful for that. We can use these methods to identify and quantitate polymer end groups, to analyze molecular weight and functionality distributions, and to characterize both primary structure as well as higher order structures such as architecture or topology of specific oligomers. Finally, we can use also this method to analyze and image surface composition and surface defects on solid polymers. And why is this information important? For many different reasons. Here I list some of them. In discovery and commercialization studies of new materials, we need to have the information I listed on the top, and so MALDI-MS and tandem mass spectrometry offer a route to this data. We can use this method again to identify unknown samples, so they are very important in reverse engineering. We can use them to distinguish similar products that have minor differences that can be sensitively detected by these methods. And finally, they are very important in elucidating polymerization mechanisms in order to improve reaction yields. This slide shows some of the widely used matrices for MALDI-MS spectrometry of synthetic polymers. These include dithranol or anthracene triol, the matrix abbreviated as DCTB, alpha-cyanoparahydroxycinnamic acid, which is shown here on the lower left, and on the lower right is DHB or dihydroxybenzoic acid. Our experience has been that the best matrix for synthetic polymers is DCTB followed by dithranol, but all the other matrices are better or worse in some case or the other, so it's always nice to have a choice and try at least two different matrices to see which one gives the better results. A question very often asked by polymer chemists is whether MALDI-MS spectrometry can be used to determine the average molecular weight and molecular weight distribution of a synthetic polymer. And the answer is yes, we can do that if the polymer has a narrow polydispersity, if it has an MW divided by MN of less than 1.3. In such a case, as shown here for a polybutadiene standard, we can derive this average data. In such a case, the MALDI-MS spectrum has a Poisson-like distribution, and then we can use the mass spectrometry data to calculate average molecular weight and molecular weight distribution. In a mass spectrum, the x-axis gives us the masses of the individual oligomers, and the y-axis the number of oligomers at a specific mass. So this data can be used to obtain the average data summarized here on the bottom of the slide, which are in excellent agreement with the average data obtained by gel permeation chromatography. By using mass spectrometry instead of GPC, we can also derive structural information from the spectrum, as I'm going to show in some of the next slides that focus on an expanded range of this spectrum. Here you see an expanded trace of the polybutadiene spectrum we saw before, showing the 37-mer, the 38-mer, and the 39-mer. We see resolved oligomers as well as resolved isotopes within each oligomer. The distance between adjacent oligomers reveals the repeat unit of the polymer, 54 Dalton in this case, which is the mass of the butadiene monomer. Once we know this, we can use this information plus the measured masses and isotope patterns to determine the compositions of individual oligomers. For example, for the 39-mer, we would expect a mass composed of 39 times the monomer plus the mass of the end groups plus the mass of the silver, and all these add up to 2272.6 Dalton, and that's an excellent agreement of what we see, both in terms of mass as well as isotope pattern. It's important to compare both mass as well as isotope pattern, calculated versus measured, when we do this kind of structural determinations. Usually when we report masses, those are monoisotopic masses, which are the masses of the oligomers containing the most abundant isotopes, carbon-12, hydrogen, silver-107, oxygen-16, nitrogen-14, etc. Unfortunately, we cannot use MALDI-MS spectrometry to determine average molecular weights of polymers with a polydispersity above approximately 1.3. An example is shown here for a polyisobutylene prepared by leaving cationic polymerization. The MALDI-MS spectra in such cases have a Schultz distribution shape with abundant low mass oligomers and a tail extending into high masses. The average data calculated from such mass spectra are very low, much lower than the data obtained by GPC. This problem arises from mass discrimination effects when we have a polymer that stretches from low mass oligomers all the way to very high mass chains. High mass oligomers are less volatile and less easily dissolved than their low mass counterparts. High-mass oligomers are also more susceptible to scattering losses. High-mass oligomers also move more slowly and therefore create less intense signals at the detector. Because of all those reasons, MALDI-MS spectra cannot be used to determine average molecular weights and molecular weight distributions for polymers with a polydispersity above approximately 1.3. Still, the spectra provide very useful repeat unit information as well as structural and compositional insight. For the polyisobutylene we just saw, the MALDI-MS spectrum shows just one distribution, one product with a repeat unit of 56 Dalton, which matches the mass of the monomer, the mass of isobutylene. The measured masses and isotope patterns of the oligomers we see in the MALDI-MS spectrum of the polyisobutylene agree well with the product which has lost hydrogen chloride to form a polyisobutylene chain that is terminated with a double bond. So we do not have anymore the tertiary chloride with which the polymer was synthesized. The loss of a tertiary chloride or tertiary halide is common under MALDI conditions. We saw that we can use MALDI-MS spectrometry to determine original or modified N groups. But can we do that also quantitatively? I'll show you an example that we can do that, and that concerns functionalized polystyrene formed by leaving an ionic polymerization. In this case, the leaving anion was reacted with an electrophile to introduce an N group, and we are going to use now mass spectrometry, MALDI-MS spectrometry, to determine what happened at the N group during the functionalization reaction. The functionalization reaction used was omega hydroxylation with ethylene oxide. So we have the leaving anion now reacting with ethylene oxide to create a hydroxyethyl N group. We have a hydrophobic polymer to which a hydrophilic N group was attached. And the question is, does it stay there, or does ethylene oxide also oligomerize during functionalization and we end up with oligomers at the N group? Extra ethylene oxide added to the N group increases the mass. For every ethylene oxide unit added, we have a mass increase by 44 Dalton. Therefore, modified product can easily be detected. In this case, the major product contains just one ethylene oxide unit at the N group, but product containing 2 and even 3 units is also detected. We can take now the intensities of the monoisotopic ions to quantitate products formed with different N groups. This slide shows the quantitation result. The percent of chains that have 2 ethylene oxide units at the chain end found by MALDI-MS spectrometry is within experimental error identical with the percentage found by NMR, which is the traditional method used for quantification. The advantage of using mass spectrometry is that we can do that to quantitate very small amounts that are invisible by NMR. A question often asked by polymer chemists who receive mass spectrometry result is, has mass spectrometry analysis changed my polymer? And that can happen sometimes, especially when we have a polymer with labile N groups. I'll illustrate this case with a polystyrene that was functionalized with a silane N group. It was produced by leaving an ionic polymerization where the leaving anion was reacted with dimethyl chlorosilane to create a polymer with dimethylsilane N group, which can be used in cross-linking reactions. A silver salt was used for the cationization of this polymer because it was a polystyrene, and silver is usually used to ionize polystyrenes. The MALDI-MS spectrum shows the narrow molecular weight distribution expected from leaving an ionic polymerization, and clearly one product, but the product detected is just the silanol. It has a silanol N group, not a silane N group. Although GPC and mass spectrometry analysis agree about molecular weight and molecular weight distribution in this case, because we have a polymer of narrow molecular weight distribution, other analytical data disagree. IR analysis shows that we have a silane, but the MALDI-MS spectrum indicates the presence of an oxidized product of silanol. Was this product formed during synthesis, or did we cause this oxidation during MALDI-MS spectrometry analysis? If such problems arise, the advice is to rerun the MALDI mass spectrometry analysis under different conditions. In this case, the spectrum was rerun using solvent-free MALDI, and under solvent-free conditions, the silane as well as the silanol are observed, as you can see on this slide. In fact, under these conditions, the silane is the major product and the silanol is a minor product. If we see the spectra change when we change experimental conditions and sample preparation conditions, this is reason for further investigation and to inquire whether something could change during mass spectrometry analysis. Silver ion is a common ionization agent of polymers that contain phenyl substituents or many double bonds. However, one has to consider that silver ion also is an oxidation agent. So the result we saw could be caused by oxidation of the silane to silanol with the silver ion. To avoid this problem, an ionization agent with a lower reduction potential than silver should be used, such as sodium. Indeed, when sodium cationization is used, the problem is avoided and the only distribution observed is that of the silane as expected from the synthesis of this polymer. This example I just discussed with you illustrates how important it is to inquire discrepancies between what the polymer chemist expects and what we see in the MALDI mass spectrometry analysis. With careful consideration of such sample preparation issues, MALDI mass spectrometry can be used for the complete characterization of polymer mixtures. In fact, for mixtures, mass spectrometry is the ideal method to use, and mixtures very often are present in raw products. So for raw products, mass spectrometry is an ideal analytical method. I'm going to illustrate you the capabilities of the method with a hydrosilation reaction, with the analysis of the raw product of a hydrosilation involving the addition of a polymeric silane, polystyrene substituted with a silane N group, to an olefin substituted with a polar N group. The product contains a polar N group attached to a hydrophobic polymer. And the question was, what products are formed? Do we only have the desired product or any other byproduct? And do the byproducts reveal any information about mechanisms, about reaction mechanisms? This slide shows the MALDI mass spectrum of the raw product. Indeed, the desired product is the major product. It is the product labeled by 1. But in addition, we see 2 more products. We see a product labeled by 2, which appears to have a slightly lower mass than the desired product, as well as a product D, which appears to have approximately twice the mass of the desired product. We can find out now what products 2 and D are by rigorous interpretation of this MALDI mass spectrum. When we rigorously interpret MALDI mass spectra, as I showed before, we look at the distance between adjacent oligomers, which reveals the repeat unit of the polymer, as well as at the mass-to-charge ratios of the individual oligomers. Here I have labeled the monoisotopic masses, which indicate the composition of these oligomers. In this case, measured mass-to-charge ratios and isotope patterns match the expected composition of the main product for the main distribution we see, where we have a butyl group at one chain end and the disilane and trimethoxysilyl N group at the other chain end. Similar analysis of the other 2 distributions indicates that product 2 is missing the polar part of the N group and contains now a terminal double bond, whereas product D contains 2 polystyrene chains and therefore appears at approximately twice the mass of the major product. Now remember, we made the desired product by addition of a silane to a reagent that contains a double bond. Byproduct 2 also contains a double bond. So now the silane can also add to this byproduct, and that explains the formation of the dimeric product. So identification of the minor products formed during this reaction allows us to derive important mechanistic insight about what happened during this reaction. Such fast analysis of a complete product mixture is very important for the development of recyclable and sustainable polymers, where many reactions have to be run in parallel under slightly different conditions, and where analytical methods are needed for the fast analysis of the raw product to be able then to change conditions to optimize the synthesis. I'm going to illustrate the approach for two cases, one concerning the polypropylene carbonate shown in this slide, which was developed by the Egan group at the University of Akron. It was produced from propylene carbonate itself using benzyl alcohol as the initiator. Under basic conditions, the polymer is formed, which is degradable to carbon dioxide and propylene glycol. So degradation leads to a polymerizable monomer, propylene glycol. That's what makes actually this polymer a sustainable polymer. This slide shows the MALDI-MS spectra of the polycarbonate obtained using two different matrices, DCTB on top and DHP on the bottom, in both cases using a sodium salt for cationization. When analyzing a biodegradable polymer such as this polycarbonate, it is advisable to avoid an acidic matrix such as DHP. With this matrix, we see partial hydrolysis and loss of the benzyl initiating end group. We end up with a polymer chain that contains propylene glycol units at both chain ends. This byproduct is also formed at trace level spontaneously because we also see that in the upper spectrum, but at much lower concentration than what we see in the lower spectrum where DHP was used. This byproduct with propylene glycol units at both chain ends can grow telechelically from both sides, and that explains the higher mass distribution that is observed in both spectra. Apart from the hydrolysis product that we see with DHP, we can say that using DCTB as the matrix, by looking at the upper spectrum, that essentially the desired product is by far the predominant product formed, and that the synthesis was successful. More information now about the intrinsic chemistry of this product is obtained by doing a tandem mass spectrometry experiment. The sodiated 20 former was used for the tandem mass spectrometry experiment, and this slide shows the fragments formed from this precursor ion. Fragments retaining the initiating chain end, the benzyl group, are labeled by letters from the beginning of the alphabet, and fragments retaining the propylene glycol terminating end group are labeled by letters from the end of the alphabet. All fragments observed fully agree with the primary structure and end groups of this polymer chain. Moreover, all fragments, and in particular the major fragments, arise by cleavages of the carbonate bonds, which are also the bonds cleaved during biodegradation of this polymer to yield recyclable monomers. So the tandem mass spectrum gives us, in other words, important information about the intrinsic chemistry of such polymer chains, which bonds are easiest to cleave. The second sustainable polymer analyzed by MALDI-MS spectrometry and tandem mass spectrometry is a polymer with locked but mechanically unlockable degradability. It was synthesized by the group of Junpeng Wang at the University of Akron, as shown in this scheme. Cyclooctadiene was reacted with maleic anilide under photochemical conditions. We end up with a polymer having a hydrocarbon backbone, to which a four-membered ring is attached, to which now the degradable functionality is appended. So the degradable functionality is in the side chain. Upon mechanical activation, the four-membered ring undergoes ring opening, and we end up now with a degradable functionality in the main chain. So we can degrade this at demand. What information can we gain about this polymer by MALDI-MS and tandem mass spectrometry? The mass spectrum of the product obtained using DCTB matrix and sodium cationization includes two distributions, a major one and a minor one. Both contain oligomers that are apart from each other by 281 Dalton, which is the repeat unit of this product. The major distribution corresponds to the desired product. The minor distribution appears 93 Dalton higher in mass, indicating the addition of aniline, probably to one of the five-membered ring imide side chains of the main product. The mass spectrum gives us information about the size of the oligomers formed, but whether the units are locked or unlocked, that is not revealed just by mass measurement. More information on that is provided by tandem mass spectrometry. This slide shows the tandem mass spectrum of a former, we see several fragments that I have labeled here in green that are consistent with the locked structure of this product. However, fragments arising from unlocked units of this polymer are also observed. I labeled them here in red. Consequently, tandem mass spectrometry conditions must cause partial unlocking of some of the repeat units, corroborating the mechanical reactivity of this macromolecule. Tandem mass spectrometry conditions provide energy that can lead to opening of some of those four-membered rings in some of the repeat units, ending up with structures with open, that means unlocked, repeat units, from where now we can form fragments that are impossible to form from the locked repeat units. Again, tandem mass spectrometry provides important information about the intrinsic chemistry of these types of macromolecules. Tandem mass spectrometry is particularly important in the analysis of copolymer sequences. I'll illustrate this with the analysis of a polyether copolymer containing two comonomers, A and B, here shown in blue and red. Both those comonomers contain liquid crystalline side chains. Now, this copolymer was formed in two different ways. In one case, monomers A and B were reacted sequentially to create a block structure, and in the other case, simultaneously to create a random architecture. The mass spectra allow us to count how many units of A and B we have in each oligomer, but they do not reveal information about the sequence. For that, we have to go to 2D or tandem mass spectra. Here we have the tandem mass spectrum of an oligomer from the sample produced through sequential addition of the comonomers, where we would expect a block architecture. The oligomer selected for the tandem mass spectrometry experiment contains 6 repeat units, 2 A's and 4 B's. The spectrum is relatively simple and allows us to read the sequence in a similar way we read peptide sequences from peptide tandem mass spectra. As I mentioned before, we name the fragments by letters of the alphabet. Those that contain the alpha substituent have letters from the beginning of the alphabet, and those containing the omega or terminating substituent have letters from the end of the alphabet. I also distinguish them here in colors. Fragments containing the initiating chain end are in red color. Fragments containing the terminating chain end are in blue color. If we start now from a fragment that contains the initiating chain end, let's say from the first red fragment on the left, the one that has a superscripted A1 that contains 1A unit, then we add an A before we start adding B's. So we started with a fragment containing 1A, we added an A before we started adding B's. Similarly, if we start from the first blue fragment on the left, the one that has a superscripted B1, we see that we add a second, a third, and a fourth B before we starting A's. So combined, these data indicate the sequence of having 2 A's followed by 4 B's, confirming the block sequence and the block sizes, actually. A much more complicated fragment pattern is observed for an oligomer from the polymer produced through simultaneous addition of the two comonomers, as shown here for the 8-mer of this product containing 3A and 5B repeat units. Now, for each fragment size, we see many different compositions consistent with the random architecture of this copolymer. Polymer architecture is another very important feature, like sequence, which is important to know because polymers in different architectures can have very different physicochemical properties. For this reason, analytical methods that can detect and distinguish polymer architectures are very important, and one of them, as I'm going to show you, is tandem mass spectrometry. Here in this slide on the top, you see a linear polystyrene with vinyl end groups at both chain ends. Metathesis ring closure can be used to form the corresponding macrocyclic polystyrene. This reaction actually also eliminates ethylene at the same time, so the oligomers in the lower spectrum should have masses that are 28 Dalton lower than the oligomers in the upper spectrum. However, mass measurement alone does not reveal architecture. We can use the masses to determine total substituents, either chain-end substituents or central substituents, but they do not reveal information about the polymer architecture. For that, we have to go to 2D or tandem mass spectrometry. Here we compare the tandem mass spectra of a linear versus a macrocyclic chain with actually otherwise very similar compositions. Completely different fragmentation patterns are obtained. For the linear polymer, the most abundant fragments are observed at lower masses, whereas for the cyclic polymer, the most abundant fragments are observed at higher masses. So just visual inspection of the spectra allows us to distinguish linear from macrocyclic architecture. We can go now and rigorously interpret the mass-to-charge ratios of the fragments observed and then find exactly what substituents we have in the alpha and omega chain and for the linear polymer, or what we have as a central substituent in the macrocyclic polymer. But the different fragmentation patterns already reveal the difference that we have between a linear polymer on the top versus a cyclic polymer on the bottom. In this slide, you can see how tandem mass spectrometry can be used to differentiate star branch polymers. We have two armed stars here. In the upper case, we have two different arms. In the lower case, two identical arms. When fragmenting the star branch polymer with different arms, we obtain two fragment distributions, one revealing the length of the short arm and one the length of the long arm. When we have identical arms, expectedly we only obtain one fragment distribution at the molecular weight of this arm. In this slide now, we compare the tandem mass spectra of star branch polymers containing different numbers of branches. In the upper case, we have a two-armed star branch polymer. In the lower case, a three-armed star branch polymer. Fragments are formed through loss of complete arms. If we have two identical arms, one is lost and we end up with one fragment distribution. If we have three identical arms, we can lose either one arm and we obtain a fragment with two arms, or we can lose two arms and we end up with a fragment with one arm. So by counting the number of fragment distributions, we know how many arms the star branch polymer has. In fact, these fragment distributions also reveal the size of the arm. The last subject I would like to cover is surface analysis and imaging using MALDI-MS spectrometry. For this, we use a solvent-free variant of mass spectrometry, of MALDI-MS spectrometry, called surface layer MALDI-MS spectrometry. It's a solvent-free variant, as I mentioned, in which solid matrix is applied only to the surface, for example, by dusting or sublimation. We avoid the use of the solvent, and this way we do not penetrate deeper layers. This way we probe only the surface, which is very important to do because it's the surface that interacts with the environment. So it's very important to know whether the surface composition differs or is the same as the composition of the bulk. The surface specificity of surface layer MALDI-MS spectrometry was proven by analyzing double layer films. And this slide shows how these films were prepared. A silicon wafer was used and a polymer layer was applied to that wafer using spin casting. On top of that bottom layer, a top layer was applied using the Langmuir-Scheffer technique that applies monolayers, only 1 to 2 nanometers thick. And different polymers were introduced either in the bottom or top layer. The ones I'm going to discuss here are polycyclohexyl methacrylate or polymethyl methacrylate. In this slide, the top spectrum shows a reference MALDI-MS spectrum of polymethyl methacrylate. The center spectrum shows a MALDI reference mass spectrum of polycyclohexyl methacrylate. Polycyclohexyl methacrylate has a larger repeat unit, and that's clearly visible by the larger distance between adjacent oligomers as compared to polymethyl methacrylate. Finally, the bottom spectrum shows a surface layer MALDI-MS spectrum of an ultra-thin polycyclohexyl methacrylate layer on top of a polymethyl methacrylate layer. As you see, we can only see the top layer, confirming or proving the surface specificity of this method. Surface layer MALDI mass spectrometry can be used to compare the composition of the surface to the composition of the bulk, which can be different, as I'm going to show you here, for films prepared from a blend of 91% polystyrene and 9% hydroxylated polystyrene. When we analyze the bulk, both distributions are observed. In fact, at an intensity ratio that very much corresponds to the mixing ratio of 91% polystyrene and 9% hydroxylated polystyrene. When we analyze the surface by surface layer MALDI mass spectrometry, the hydroxylated component is not observed anymore. It has segregated away from the surface. We also see the average molecular weight dropping down. We can conclude from this comparison that shorter chains are entropically enriched at the surface and that the hydroxylated chains, the polar chains, are depleted from the surface, information that is very important to determine the properties of surfaces prepared from blends. Surface layer MALDI mass spectrometry can be also used to image polymer surfaces and detect defects. This can be done to detect the presence of foreign material or the absence of material or mechanical scribing and scratching or solvent perturbation, and I'm going to show you here a couple of examples concerning the presence of foreign material and mechanical scribing. And those experiments were done on surfaces made from 7 kilodalton PMMA or 6 kilodalton polystyrene. This slide shows foreign material defect analysis by surface layer MALDI mass spectrometry imaging. What was done here was a polystyrene stamp was applied onto a polymethyl methacrylate film. The optical image shows the defect, but the SL MALDI image not only shows the defect, but also the chemical composition around the defect and on the defect. Around the defect, only polymethyl methacrylate is detected, as shown here. On the defect, only polystyrene ions are detected. So by using SL MALDI imaging, not only we can visualize the defect, but also determine its chemical composition. Finally, this slide shows SL MALDI images of defects created on top of polymethyl methacrylate films. The defects were created by scratching the University of Akron logo or by etching, laser etching, either the logo or the mascot of the university's football team. In all cases, the SL MALDI images nicely reproduce the defects. Moreover, the SL MALDI images also provide information on the chemical composition around the defects, which is obviously not available with the optical images. How clear the image is depends on the resolution of the instrument. Our instrument has a 200 micron resolution, which is a Bruker Ultraflex, which gives an acceptable image of the defect. However, superior resolution can be obtained with a higher scale imaging instrument such as the Bruker Rapiflex tandem time-of-flight mass spectrometer, which has a resolution of 35 microns. Let's finish with a brief summary of the capabilities of MALDI mass spectrometry and tandem mass spectrometry. In the last 40 to 43 minutes, I tried to show you that these methods combined offer the possibility to achieve a complete compositional and structural characterization of polymeric materials. With complete characterization, I mean sensitive identification of not only the major products, but also minor products, which reveal important information about reaction mechanisms and the commercial viability of the product. I showed you how we can use tandem mass spectrometry to analyze not only primary structure and end groups, but also copolymer sequences and polymer architectures and topologies. We also saw that we can use tandem mass spectrometry fragmentation patterns to derive important intrinsic information about the chemistry of the polymer under study, as we saw in the mechanically lockable, unlockable polymers, where the tandem mass spectra revealed information on which bonds break preferentially. Finally, I showed you that we can use MALDI mass spectrometry to analyze and characterize polymer surfaces and defects on polymer surfaces. Overall, these analytical capabilities improve significantly our ability to characterize the microstructure of synthetic polymers and allow us to more confidently answer analytical questions in polymer science. Before finishing, I would like to thank my collaborators, the students who measured the data I showed you today. I encased in green squares the students who significantly contributed to the results I showed you today. And these students include Alir Yol, who now works for Avery Dennison, Kevin Endres and Jeline Mao, who both work for DuPont now, Savannah Snyder, who joined Bruker in the summer of 2020 after graduation, and Kyla Pavlantos, who is still working with me and will be graduating by the early next year at the latest. I would like to thank these students, all the other students in the group for their hard work and help, our collaborators, as well as our funding sources, Bruker for enabling this webinar, and all of you for attending this webinar. I would be very happy to answer any questions you might have. Thank you very much indeed.
Thank you, Chrys, for that very interesting presentation. We've gotten a lot of questions, and we'll take as many as we can. To start off, someone asked, when is GPC a better option than MALDI-TOF?
That's an excellent question. If you want to measure molecular weight distribution, then if the polydispersity is above 1.3, use GPC to measure the molecular weight distribution. But if you want information on the composition, you still should run MALDI. The MALDI will not show peaks at the average where you would expect them. It would show peaks at low masses, but still it would give you information about what N groups you created. But if the distribution and the average molecular weight was desired, then run GPC.
Great. Thank you for that answer. Someone else asked, can you please tell a little bit more about the resolution of spectra in both the MS and MS-MS modes?
Again, excellent question. Usually the most modern instruments that are used in these experiments are either MALDI-TOF or MALDI-QTOF, quadruple time of flight mass spectrometers. And in both cases, the mass analysis in MS mode, in mass spectra, and in MS-MS mode, in tandem mass spectra, is done by a reflectron time of flight. So we have high mass accuracy in both cases. And the resolution, if you have a quadruple time of flight mass spectrometer, is going to be better than in TOF mass spectrometers for tandem mass spectra. But the mass accuracies are going to be quite high in both.
Thank you. Someone else asked, does MALDI-MS also require polydispersity?
No, you don't have the restriction for MALDI-MS, because there, whatever you see, and it will be the Schultz distribution. Now remember, if you have high polydispersity, you are not going to see the Poisson distribution or the Gaussian distribution you have. You are not going to see the bell-shaped curve that you have when you have an arrow. You're going to see the Schultz distribution, then you take one of those peaks and you do tandem mass analysis on them. Very often, the tandem mass analysis of the low mass and the high mass oligomers is very similar. Now, sometimes you form a linear product and a cyclic product, and it could be that at the low masses, the cyclic product predominates. So you cannot do a quantitative analysis of the peaks, but the peaks that you see at high polydispersity, you can still take them and analyze them by tandem mass spec. There is no limitation for that. And that's the beauty, actually, of tandem mass spec.
Great, thank you. We have another question now. This is a multi-part one. So the first part is the peak intensity directly proportional to the abundant number of oligomers present or to the stability of the oligomers? Mm-hmm. If it depends on the stability, are the larger polymers broken and only small oligomer peaks will be intense? Is that right?
Yeah, I understand the question. So usually, in very few cases that MALDI causes fragmentation. In most cases, all the things that you see are molecular ions. And if you want to cause fragmentation, you have to do that in the tandem mass spectrometry mode, if you deliberately want to do that. So even large or small oligomers have comparable stabilities. Remember, a polymer will tend to fragment if it has weak bonds. So if you form something by raft or by a polymerization method that contains carbon-sulfur bonds, then whether the mass is high or low, it's going to break. Whether a polymer breaks or not, it depends on whether you put enough energy to equate what's needed for the dissociation energy. And so larger polymers, you need to input actually more energy to accumulate enough energy to dissociate them. They dissociate, in some cases, it's more difficult to fragment larger polymers when they're singly charged. So, I mean, to, again, simply summarize your question, which is a very important question, usually what you see is all molecular ions. And so if you don't see a Gaussian distribution, it means that the polymer is not of narrow molecular weight, of narrow polydispersity. It's broad, and that's why. It's not because it's fragmented. Actually, in that case, you can use electrospray or another method, and you actually can confirm what I just said.
Okay. Thank you for answering that. Someone else asked, are derivativization reactions used to confirm the structures?
Yes, they are, and a derivatization reaction, guess what it will do? It will change the end group. Changing the end group, every reaction that changes the mass must be the ideal method to monitor it and to probe it. Derivatization reactions that don't change the mass, I mean, that could be a little bit more challenging. That's where then you must do tandem mass spectrometry. But even simple mass spectrometry, when you derivatize, it will show you, like you methylate, the peaks should shift plus 14 Dalton. You acetylate, they should shift plus 42 Dalton. You phosphorylate, plus 80 Dalton. Or you add something else, it will be the mass of that reagent that was added to the chain end. I mean, you have to remember also the reaction mechanism. You may add something, you may eliminate, say, water at the same time, or something else. So there'll be a mass increase usually in the derivatization, and mass spectrometry is ideally suitable to monitor that because it changes the mass. And the method is called mass spectrometry. So that's actually where it's mostly used, mass spectrometry, to check changes in mass, in addition to confirming, obviously, what was synthesized. I hope that answered that question, I think, but I think that was whether derivatives can be. Yes, it's used, and mass spec would be the ideal way of checking or whether derivatization works.
Great. Thank you. Another person asked, if the polymer is soluble in water or organic solvent, would it be possible to analyze high molecular weight and higher than 1.3 polydispersity?
No, that doesn't have to do with the solubility. Actually, you should choose the solvent that works best for your polymer. And if the polymer is water soluble, use water as your solvent. You don't have to dissolve polymer and matrix in the same solvent. You can use different solvents. That's another beauty of MALDI. You don't have to have a solution. You make this solid mixture, so you can dissolve your polymer in water, apply a droplet on the MALDI plate, then you can dissolve your matrix in an organic solvent and apply it on top. Or you can apply matrix on the bottom, put then the water solution of your sample, and another layer of matrix on top. That's the so-called sandwich method. You can choose whatever solvent you want. It's not going to change the problem I mentioned in my talk, that if the polymer has a high polydispersity, you're not going to see the molecular weight distribution. Whether that's water-soluble or THF-soluble, it doesn't matter. That's because of the discrimination effects that we have, which are the same, independent of the solubility of the polymer. The longer chains are always going to be more difficult to dissolve and to transmit, and they'll scatter more easily, and they'll give lower signals at the detector. So those things are the same, whether the polymer is water-soluble or soluble in an organic solvent.
Thank you for that. You may have answered this already, but just to be clear, someone asked, why can we not use MALDI-TOF for polymers that have polydispersity above 1.3?
Thank you for that question, because I want to clarify that you can and you should use MALDI for structural and compositional information. You cannot use it to determine molecular weight distribution. So if somebody comes to you and says, I want to know the average molecular weight of my polymer, and if that average molecular, if the distribution of the polymer is broad, then tell that person use GPC for that. But if that person came to you, the synthetic chemist or synthetic polymer scientist, and he or she told you, I want to know what N groups my polymer has, by all means, run the MALDI-MS spectrum. Whether it's broad or narrow, it doesn't matter. You still are going to get information about the N groups, about the derivatization, the reaction that the answer that I gave before. You can use MALDI for those things. You just cannot use it to determine average molecular weight and polydispersity if it's broad. But everything else you can still do. The analytical, the compositional analysis you can still do. The N group analysis you can still do. And actually in my talk I showed that with the polyethylbutylene. I mean, we couldn't measure the average molecular weight, but we could still determine the N group.
Okay, we have a question related to N groups. Someone asks, what is the mass fraction required to see an N group? Or to put it another way, above what molecular weight can an initiator N group not be identified?
Excellent question. I mean, you can, that's the problem of bulk methods, that you have to have a concentrate, that the N groups have to be a specific, quite a bit of a percentage of the mass to detect them. But with mass spectrometry, even if they are a small part of the polymer and they affect the mass, you are still going to see them. So let's say, I mean, obviously to be able to identify N groups, you need to have oligomer resolution. Let's say we have a polymer, a polyester with 200 repeat units. That would be butylene terephthalate, for example. 200 repeat unit, I made it big, that assuming then around 20,000 molecular weight, will be able to have oligomer resolution. Even if we change the N group by 1 Dalton, from OH to NH2, we should be able to see that, and we can see that. So if that was the question, if your question was what percent can we detect with mass spec, then I would say, let's say you have a mixture of N groups. You could go with mass spec down to the parts per billion. That's the difference now from NMR. That's what I was trying to convey with the table I showed in my talk. If you have, say, a polymer that can have N group A and N group B, you can see B now, even if it was at the parts per thousand or parts per million level. It doesn't have to be high, because mass spec, the dynamic range is high and it's a very sensitive method, and because part B will be at a different mass. There will not be overlapping. So that's another advantage of using mass spectrometry for those questions instead of another technique that looks at the bulk.
Great. Thank you very much. I think we're going to stop there. I will let the audience know that if we didn't get to your question, the questions will be passed along to Chrys.
Yes.
And well, thank you again, Chrys, for your fascinating presentation and the great interest from the audience.
Thank you, Anne, for organizing it.
Yes. Please be sure to check CNN or CNN Online for information on the next edition of CNN webinars. Our thanks to On24 for technology and production services, and thank you, Bruker, for the sponsorship that made this interactive webcast possible. For CNN webinars, I'm Ann Thayer. Goodbye.
Goodbye.